Hello everyone, this is Dr. Chantel Marshall, and this is the lecture for Psychology 210 covering the t-statistic for related samples. You should have already watched a lecture covering the basics of the t-statistic, and this will give us a more specific t-statistic for a special data set that we might be working with. In this lecture, we will go over the related samples designs, of which there are two. The first is a repeated measures design, where we have the same group of people and we simply measure them on our variable of interest at time 1, some time that we decide, and then later on at a different time, which we call time 2. So this is the same group of people measured at two different times. This is the more common related samples design that researchers use. But another design that researchers might use is called the related samples or matched subjects design, in which you compare two groups that are matched on some variable that you find important. And I'll go into more detail on that later on. Then, of course, I'll introduce you to the formulas for the t-test for the related samples. This will look very familiar to those of you who've watched the lecture covering the basics of the t-statistic. The formulas look very similar, but are different, of course, because we're using a different design. I'll cover effect size, which is very similar to the way that we do it for the regular t-statistic. And then I'll walk you through the steps of hypothesis testing with the related samples t-statistic. So remember that the whole point of learning all of these different ways of testing your data are to conduct hypothesis testing, and simply replacing whatever tests you conduct in that hypothesis testing procedure with the one that matches best with the kind of data that you have. So in the original t-statistic, we were dealing with a sample from a larger population where we might be able to guess the mean of that population, but now we're going to look at a slightly different type of data, and so therefore we have to conduct a slightly different test to look at those data. Okay, so let's think a minute about putting together an experiment using related samples. And this example that I'm going to show you uses this time 1, time 2 setup. So as you all probably remember, your independent variable for any experiment is what is manipulated by the experimenter. So this is what the experimenter believes to be the cause of some sort of effect. And the way to test whether or not this variable is in fact causing a difference, we have to manipulate it and give it different levels. Okay, so we can do this in various ways, but as long as it's being manipulated by the experimenter and as long as it's the suspected cause of an effect, it's our independent variable. And we're thinking that it causes the effect on what we call our dependent variable. So after we've manipulated our independent variable, we have participants fill out a survey perhaps, or we watch their behavior, and we're setting out to see if that manipulation that we did in the IV then produces an effect in the DV, right? And so that's why it's called the dependent variable. Its level should depend on the independent variable, okay? All right, so the way that we would put the study together with a related samples design is by having one group that serves as the control condition. So the group receives no treatment at time 1. Okay, so you bring them in as is, you measure them on whatever variable it is that you're interested in, and that's it. Now, the way that we manipulate the IV is then to have the same group receive a treatment, and then we measure them at time 2. Okay, so keep in mind that with this related samples design, this time 1, time 2 design, we're using the same group of people at different times. And those different times are associated with different levels of our manipulated independent variable. So we'll walk through an example so this makes a little bit more sense to you. So the advantages of having a related samples design over other designs, for example, an independent design, which you either have learned about or will learn about, are actually quite a few. So one is that you don't need population parameters because we're comparing two groups or two time points that we are in control of. We're not as concerned with the population overall in terms of getting their actual parameters. We can look at study changes over time. So this is a longitudinal type study. So even if time 1 and time 2 differ by a day, we actually can look at any changes in time that have happened over that time period. But again, we can make this time 1 and time 2 actually much farther apart. So we can have it one day, we can have it a week, we can have it a year. So we can start to look at perhaps how time may affect our dependent variable. And really importantly, the related samples design, and the reason why we tend to use it is because it controls for individual differences. And this is a big deal because individual differences can often give us a lot of problems as researchers. So many of you, when you think about setting up a study, you think, oh, well, we didn't take into consideration their height or their normal health. We didn't take into consideration whether they wear glasses, how much they drink. We didn't take into consideration how old they are. You know, all of these random variables that we are not taking into account. And you all are right. We don't often take those into account. And so this design allows those differences to basically wash out because a person will have, for example, the same health at time 1 and time 2, right? Because we're looking at the same person. So we don't need to look at how our groups might vary on those individual differences. So if we want to say this in statistical terms, using one person at time 1 and time 2, it eliminates the standard error, right? Which we want as little standard error as possible. It eliminates the standard error that's due to noise or these individual differences that we're simply not interested in, that really aren't related to the IV, right? So one thing, for example, is age. If age is not a variable that we're interested in, it's just random noise that's possibly causing some error that we don't care about. This allows us to not worry about that individual difference that might cause a difference in our DV. Okay, so it eliminates some of that standard error, which is always good. We're always trying to eliminate as much standard error as possible. And finally, a smaller sample size is needed to carry out this research, which in practical terms is great because to get a research participant can sometimes be really hard. It can also take up a lot of resources. It might take up a lot of time. And so the smaller the sample size that you need, the better, because you're able to do it more quickly, you're able to use fewer resources, things like that. So using a smaller sample size or needing a smaller sample size is good, right? Because as we all know, the bigger your sample size, the better. But if you don't need as big of a sample size, then that's even better. All right, so let's look at a research question that we can look at using this related samples design. So if you watched my lecture on the t-statistic, then this is going to look very familiar to you. And I did that on purpose. I want you to see how we might look at the same question using different types of designs, right? And so as a researcher, we get to decide this, and this is where the art might come into play, right? So do I want to use a related samples or not? Do I want to use a scale or not, right? How do I want to recruit the participants? All of that is really up to the researcher. And so the design that you choose will basically set up what statistical test you use. And so often as researchers, that's one thing, especially new researchers forget, is that you have to be able to analyze your data. So you need to set up a design that you feel very confident you can analyze the data for. So we're walking you through a few different ways to set up a study and how you would look at the data when it's done. Okay, so if you're interested in whether American men over the age of 35 get better sleep if they exercise regularly, you might want to use a related samples design. So as we talked about before, the treatment for this is regular exercise. And our dependent variable is sleep quality. So we're trying to see if our IV of exercise or not affects, right, how well these men sleep. Now, instead of taking a sample from the population and comparing that sample to the population or two groups that get different treatments to each other, we're going to compare the same group of men. Okay, we're just comparing them at two different times. So at time 1, we'd simply bring in our participants and say, how well do you sleep? And that's it. And then we would introduce a different level of our independent variable, right? So at time 1, the level of our independent variable is no exercise. Okay, so we're bringing in men who don't exercise regularly. That's our baseline. And then we ask them to start exercising regularly and then bring them in again at time 2, maybe a few months later, to see whether or not their sleep quality has changed. And I think that this design is intuitive to most students, that you would see, oh, okay, first we'll get people who don't do this regularly, measure sleep, and then we'll have them do it regularly, and then we'll measure sleep again. So this is pretty intuitive, I think, in terms of how to study this cause and effect relationship. And so we're just going to figure out how we would then analyze our data to see if there's actually an effect of the treatment that we have put together for these participants. Before we get into that, though, I want to talk about these two types of designs that we could potentially use. And one I've already introduced to you, and like I said, it's the one that most researchers who use related samples choose to use for their studies. Okay, so this is the repeated measures design. It's also called the within subjects research design. Okay, so these mean the same thing. Okay, so repeated measures, you're repeating a measure at time 1 and time 2. Within subjects simply means that all subjects go through all of your levels of your independent variable. Okay, so they see all the levels, not just one. And so here our dependent variable is measured 2 or more times for each individual in the sample. Okay, so we're not going to get into 3 or 4 or 5 times. We're just going to do 2 times for now, because 3 times starts to get really complex, and unless you're going to run a study like that, you really don't need to know how to conduct those statistics. And like I said, and like you saw in the last example, the same group is used in all of your treatment conditions. So they come in, you measure their sleep quality, and then you have them exercise, and then you measure their sleep quality again. So this is my representation of what men who don't exercise regularly do. I don't know. So maybe, they come in, they're just, instead of doing exercise, they're playing video games, right? So that's time 1. And then you say, hey, maybe you should exercise. Maybe you give them like an exercise machine, or you buy them a gym membership or something, or you bring them in with a trainer, and then you have them, again, exercise maybe 3 times a week. Remember, this is your operational definition, however you want to define regular exercise, and then they come in again and tell you how well they're sleeping. So with this repeated measures, one group's DV is measured twice. So after the first level of your IV, in our example, it's no exercise. And then after the second level of your IV, in our example, it's regular exercise. But there are some problems. So again, this might seem a very intuitive design to conduct research, but there are some problems that you want to make sure that you address within your design. One of these is, and I would say the biggest one, is order effects. All right, so if everyone is given the levels of the independent variable in the same order, it could be that that specific order of the levels is what's causing some of your effects. So basically, it could be that level 2 is affected by level 1 coming first. So let me use our example to explain this a little bit further. It could be that regular exercise does in fact help sleep quality, but only for those people who were previously not exercising. Hopefully that makes sense. So it could be that sleep quality is only affected by exercise if you haven't been exercising regularly, right? So maybe after a while, that exercise doesn't have the same effects on sleep quality, right? So it could just be that change going from no exercise to exercise that improves sleep quality, not the actual exercise itself. So in order to address this problem, we do something called counterbalancing, which basically means don't give everyone everything in the same order. You might want to mix it up to make sure that it's not the order of your levels that's producing your effect on the DV. Okay, so in our example, this would look like this. So if we are bringing in, let's say, 6 participants, which we probably wouldn't do because it's a very low number, but it fits in the table. This is what, the regular sort of design would look like. We would have participants coming in, let's say participants 1 through 3 come in at time 1. They don't exercise regularly, right? And so you just say, oh, how's your sleep quality? And then you have them exercise regularly, and then you measure their sleep quality again. It's the same design we've gone over a few times already. But when you counterbalance, you have to make sure that another set of participants gets the opposite. The opposite. All right. So for them, you would bring them in and have them exercise regularly first, right? So let's say maybe for like a month, measure their sleep quality, and then you have them stop the exercise for a month, and then you measure their sleep quality. I don't know why that word exercise looks to me like it's not spelled right, but so that's what I mean by counterbalancing. Okay, so you have level 1 and then level 2, right, of your IV, levels of your IV, level 1 and then level 2, or level 2 and then level 1. Okay, so this, if you get the same effect, if you still get that men over the age of 35 are getting better sleep when they exercise, then you know it's not an effect of that change, right? It's just an effect of the actual exercise itself. All right, so this is a good way to deal with this problem using repeated measures design. However, there is another design that is sometimes used, and this design is actually a little bit more popular with drug studies, I will say, not as much with, let's say, like behavioral studies, all right, but it's definitely a design that's available to all researchers if that's the way they want to go. So instead of having participants in the same group who are measured at level 1 and level 2. Instead, each participant in one sample is matched with a participant in another sample. So this is also another way to get rid of those individual differences. So if you think, oh, well, if I'm looking at exercise and how it affects sleep quality, I really think that age is going to be a factor. So in order to make sure that is not causing all this noise in my data, I'm just going to make sure that for each participant of a certain age in one group, I'm going to have another participant of that same age in the other group. Okay, so if someone is 42 in my sample who's getting exercise, I also need someone who's 42 who's in my sample who's not getting exercise. And that way, that age difference you don't have to worry about because you have the same ages in your first sample as you do in your second sample. So in this case, there are 2 actual groups. So you match the participants on some variable that you think might cause some noise, okay? So the groups are equivalent on that variable. So an example is age, like I just gave you, perhaps work hours if you're looking at work stress or something, region in the country if you're looking at social attitudes like I do a lot. So where people live in the country actually has a lot to do with how they think about government and how they think about certain social groups. And so again, you're trying to reduce the noise in your data. You're trying to reduce that standard error. So in this case, instead of having one group that's at time 1 and time 2, you have 2 groups, but they are matched on some variable. And back in the day when I was learning about this design, they were called yoked participants, which I actually really like that word, because yoked, if any of you grew up on a farm or a ranch, you know what this means. So this is when you basically pair, right, 2 animals with this sort of contraption so that they can't go in different directions, right? So if they're pulling a cart, they have to go in the same direction. I like the word yoked because it brings to mind this contraption. I'm like, ah, yes, the participants are yoked. They are matched. They are going in the same direction. But I don't know. I don't know if everyone thinks the way I do. In fact, I'm pretty sure not a lot of people do. But the matched subject design is also called the yoked subjects design. So the participants are matched on some important variable that you think might add noise or going in opposite directions into your data. Okay. All right. You guys can see I get really excited about research design, research in general. So you're going to use the same statistics as your repeated measures. The design is different, but the way that you carry out the math is exactly the same. So clearly you have to pay attention to which design you use, but in terms of the actual math, you're going to be using the same formulas. So what do these data look like? So let's say that I have my 1 participant. We're using repeated measures now instead of the matched participant or yoked participant data. So let's say that I have this one, we're just looking at 1 participant who was in my study, who I brought in, doesn't exercise regularly, figured out his sleep quality, and then he exercised, right? So the same participant goes from no exercise, I measure his sleep quality, to exercising regularly, and I measure his sleep quality again. Okay, so repeated measures, we just went over it. So at baseline, let's say that his sleep quality is a 3.6. And remember, so we're using the same scale as we did in the other lecture, where 1 is horrible sleep and 7 is amazing, beautiful sleep. So this person is experiencing not that great sleep. It's below the sort of middle, so he's not that great, but it's okay. So that's baseline. After exercise, his sleep quality goes to a 3.9. So you as a researcher might think, oh, here it is. Evidence that exercise greatly increases sleep quality, right? So our difference is 0.3, right? So we took that 3.9 and subtracted 3.6 to get what we call a difference score of 0.3. And I want you to pay attention to this, because when we're looking at repeated measures data or matched participants data, what we're interested in is not this. What we're interested in is this. How different are those scores? Because as a researcher, we're expecting a significant difference, right? Something that is statistically significant. And so we're really interested in that 0.3 more than that 3.9. So that will be what we end up analyzing. So that difference score we're going to represent with that capital D, okay? And we're going to take the raw score, so our X is back. We're going to take the raw score at time 2. I want you to pay attention to this. The raw score at time 2 and subtract the raw score at time 1. So in our example, X2 is 3.9 and X1 is 3.6, which gave us that difference score of 0.3. And this formula of keeping that time 2 first is important. Okay, so sometimes students think, oh, it doesn't matter, I'll just As long as you subtract one from the other, you get a different score. But in this case, the order really makes a lot of difference. So we need to keep it in this order. So the second time point comes first. Okay, second time point comes first. And basically the second time point should be the equivalent of the introduction of your cause. Okay, so in this case it would be exercise. All right, so even if you counterbalance, the second time point should be the introduction, the experimental treatment group. Okay, so this is because when you get a positive difference score, so this 0.3 here is positive, it indicates an increase. Okay, and remember, we're in this case looking for an increase. And so that 0.3 is good. We're looking for an increase. And a negative difference indicates a decrease. So let's say, for example, that participant 2 went from a 4.0 to a 3.5. Okay, so in that case, his difference score would be, anybody? 0.5, right? So we would take that 4.0 after exercise and subtract the 3.5, which was his baseline, and we get a negative 0.5, right? A negative 0.5. So that negative difference indicates a decrease, okay? And so that's why this formula order is really important, because the positive difference score will tell us if it's an increase, and the negative difference score will tell us if it's a decrease. All right, so I hope I made that point very clear, because I hate to take off points when this order is incorrect. It breaks my heart. It breaks my heart. Okay. All right, so what we're going to look at is the mean of those differences. Okay, so instead of adding up all of these and figuring out their mean, we're going to add up all of these and figure out their mean. All right, so we're just going to sum all of our difference scores and divide by the number of scores that we have, or the number of people in our sample, to give us our average difference score. So on average, how different were the scores from time 2 and time 1? And mu d is the mean of the difference scores. Okay, so this is what we're comparing against, right? So this is the population mean of the difference scores. Okay, so these are all of the different statistical pieces that we're going to need as we move on to figuring out how to calculate our t-statistic using a related samples. Okay, so let's look at our hypotheses for the related samples t-test. So as always, we have to state our null, right? Because we're always testing against our null. So our null is sadly that our population difference scores would be 0, right? So remember that our sample is always representing our treated population. In this case, it represents, the difference between the treated time and the non-treated time. So our null hypothesis would be that the difference between time 1 and time 2, so at time 1 they're playing video games, not exercising, and at time 2 they're exercising regularly, that the sleep quality difference between those two times is nothing. They're still sleeping not so great or whatever, right? And so again, we are hypothesizing that the population that our sample is meant to represent has differences of nothing, right, in our null hypothesis. But of course, we always have to state the null hypothesis. We have a few alternative hypotheses that we could be comparing to the null, and I'm just going to list them all at the same time. And it's basically whether you're hypothesizing an increase or decrease, or have no direction to hypothesize, as we have talked about before, right? So you can either be hypothesizing in a direction or no direction, and of course that's going to change whether you're going to conduct a one-tailed or a two-tailed test. So you can either hypothesize that your differences between time 1 and time 2, or between your matched participants, is not 0. So there's some difference in there, Or you can hypothesize that that difference is positive, is basically positive, so that you get an increase in some variable. In this case, that would be our variable of sleep quality. Or you can hypothesize that there will be a decrease, in this case, that your difference would be negative. Okay, so remember, a positive difference is an increase. A negative difference is a decrease. So that might be something like blood pressure for a blood pressure medication, right? You're expecting that the difference in blood pressure from time 1 to time 2 is going to be negative because you expect a decrease. Okay, so you can have any of these three alternative hypotheses. And the t resembles the single sample t-statistic. So you remember that looked a lot like the z score, except that we were using estimated standard error because we didn't have our population parameters. So it's going to look very similar, except you're going to see an addition of an extra letter. Okay, so we are taking the mean difference that we calculated against the population difference, and we'll get into that in just a second. And we're going to divide it by our estimated standard error of the differences. Okay, so remember, everything we're working with in the related samples t-test is about those differences between your scores, not the actual scores, but the differences, how much they've changed over time, which is why we have this D to demarcate everything. That instead of using just those raw scores, we're actually using the differences between those raw scores. But once you've calculated those differences, it all works pretty much the same way. Okay, and to estimate our standard error, again, this looks a lot like our single sample t-statistic. We're going to take our variance, divide it by n, and then take the square root of all of that. And that gives us our estimated standard error of the differences. And the reason this works is because when we take our variance, it's the variance of those differences. So you don't have to do anything special. As long as you're just working with the differences in your data, you don't have to do anything else. Okay, that D is just reminding you that these are not raw scores. They're differences between two raw scores. Okay. All right, so hopefully when we go over the practice and when you practice on your own, that will become a little bit more clear. Okay, so you can also figure out your standard error by taking your standard deviation and dividing by your square root of n. So for those of you who are like, wait, what? Okay, so remember that this is the same thing as this. These are, in mathematical terms, saying the exact same thing. So when you take the square root of a fraction, you can just take the square root of the top and take the square root of the bottom. In this case, if you take the square root of the top, you're canceling out that square, right? And you're just left with standard deviation. For those of you who have not heard my joke about this, what do you get when you put root beer in a square cup? Beer, right? Because the square root cancels out the square. Okay, so basically this cancels out here. We get an S, but we still have to take the square root of the bottom part of the fraction. So again, these are equivalent mathematically. So it's just about whichever one you prefer, or if you have your variance, you would want to use this, but if you have your standard deviation, you would want to use that one. Okay, and of course we need our degrees of freedom because we are running a t-test, and that will, as always, be n-1. Right? So we will work with some data in our practice looking at how to use the different scores instead of the raw scores to figure out your t-statistic. And our estimated Cohen's d is super simple. In this case, we're just using the mean difference that we calculated for here, and we're dividing it by the standard deviation of our sample. Okay, so if you want to get Cohen's estimated Cohen's d, you would simply take the mean differences of your related samples design and then divide it by your standard deviation. However, if you wanted to use R squared, it would look exactly the same as when we ran it with the single sample t-statistic. And so that is, as you probably remember, how much of your variability is explained by your IV. So in this case, R squared can explain how much of differences in sleep quality are due to exercise and not to confounds, to sampling error, to random noise, etc. Okay, so it's going to give it to you as a percentage. Okay, so again, we are simply using our t value that we calculated and putting that into this equation. And our magnitude of R squared hasn't changed. So if it's 0.01, we have a small effect, a 0.09, a medium effect, 0.25, a large effect, and 0.50, or larger, a very large effect. So we'll be using the same effect sizes, either estimated Cohen's d or R squared, with our related samples. So finally, let's go over hypothesis testing with our related samples t-test. So as always, we have our null hypothesis, that is that our mean differences in our treated and untreated populations are 0, so there's no difference. And then we have our alternative hypothesis, which is that our mean differences are actually not 0. Okay, and of course we can also hypothesize either an increase or a decrease. So an increase we would expect a positive difference, and a decrease we would expect a negative difference. You set alpha, so standard is at 0.05. Of course, if you want a more conservative test, you want to lower our probabilities of committing a type 1 error, then you can set your alpha lower. You find your t-value using the formulas that I just gave you. You check to see if it's in the critical region, given your alpha and your degrees of freedom, right? So here is a potential set of numbers we might use to see if it's in the critical region. And finally, you decide what to do with that null hypothesis. Remember, we're always testing against that null hypothesis. And so you either reject the null or fail to reject the null. All right, so one thing that I want you to keep in mind is that because we are always testing against that null, our best guess for the mean of our population differences is actually 0. So I'm going to quickly go back to our other slide. So when you look at this slide, you'll notice that we can easily get our mean differences. We just take time 1 data, right, and time 2 data, and we subtract time 1 from time 2, as I showed you. And we can easily get our estimated standard error by using one of these 2 different formulas. But we don't have is this, right? The population differences, the population difference scores. And because we're always testing against the null, that our best prediction for that is actually 0. So when you go ahead and start calculating your own t-statistics using related samples, you're going to take your mean differences that you find from your sample and subtract 0, basically, because that is our best estimate for the differences. And because we're always testing against the null, right? We're always testing to see if our mean difference is bigger than the null mean difference, which in this case would be 0. Okay, so we're going to take our mean difference, subtract 0 from it. I know it seems kind of redundant and weird, but this is how we set it up because theoretically this is how it works. And then we divide by our standard error, which will give us our t. Okay, so when you go ahead and try the practice on your own, you want to set that mu d as 0 because that's what we're testing against. We're testing against that null hypothesis. So that's it for the lecture. Of course, there will be practice problems that you can also watch and follow along with so that you can make sure that you're on the right track. So good luck with your related samples t-test. I am still a big fan of the t-statistic, and I hope that you all are also becoming big fans at this point. So good luck with your practice problems, everyone.